one more last distribution. We skipped, I think we're chapter 14 in the book. So the last couple weeks of class, I think we get up to 10, and then I skip to 14. And then the one next week is 12. But that's already available for you online. New distribution today. This is called the ChiSquare distribution. And for those of you who came in, did I get everybody has one? Okay. You take a look at this curve. This curve is not a normal curve. It has some of the tendencies of a normal curve in that it has one hump, but it is not a symmetrical curve. The other thing about the chi-square curve, if you notice, the value starts at 0. If you're doing some work and you ended up with a negative chi-squared, stop, take a break, and try again. Because a negative chi-square value is impossible. He really screws it up. Okay. We're going to use a chi-square statistic when we have data that is nominal in nature. Right? Nominal data. So our dependent variable of interest is a name or some sort of group. Let's just start with an example. Let's say we give you a personality test. And there's tons of personality tests out there. There's this thing called Myers-Briggs. Have you ever heard of that one? Where you're like an LPTV. Yeah, it's a thing. I think it's all garbage, but whatever. Have you heard of your astrological sign? What are you? Anybody want to guess what I am? Nope. Close. Nope, nope. I'm a Taurus. Why do you think I'm a Taurus? Okay. I'm stubborn. Yeah. That's okay. It's all right, Sammy. You're so close to graduation. Nothing's going to screw you up now. There you go. Again, let's classify your personality based solely on the day you were born. And it's not even by month. It's like the 22nd to the 23rd of the... It's stupid. Why? All right. So here's an example from the textbook. We're going to categorize our participants into one of 4 personality types. Now, you've probably heard of alphas and betas before. Right? This whole concept of leaders and followers. And then there's also gammas and deltas. Gammas and deltas have the same introvert-extrovert pairing. So a gamma is like an alpha in that it's extroverted, but instead of norm favoring, it's norm questioning. So they're your rebels. And your deltas are introverts who are also norm questioning. These are the followers of the rebels. People who got the tattoo because somebody else got the tattoo and it was cool. I don't know. Again, I don't believe in any of this, so I'm kind of just going along with it. So I look at you, and I'm like, Allie's a something. What do you think you are, Allie? An alpha, beta, gamma, or delta? Okay. Again, all this is garbage. So we've got about 600 students, and it turns out a lot of students are alphas or gammas, and not a lot of students are betas or deltas. Okay. What the chi-square is designed to do is to look at the distribution of your data and to see if it is what we would expect. Now, just looking at there's no dependent variable here, right? It's just one thing. So the first question is this evenly distributed? This is back to this question of our sample, right? How likely are we to get a sample that has this distribution if in the population personality type is evenly distributed? If personality type were evenly distributed, what would these bars look like? They would be equal. Yes, thanks for repeating what I just said. The bars would be flat. Well, all these bars are flat. What are you trying to say? Equal height across the board at any particular spot? Thank you. It's a statistics class. Feel free to use numbers. If these traits were evenly distributed in the population, we should have 4 bars. The fact that my hand is blue somehow is making me even worse of a drawer. We would have 4 bars that are equal height, right? Right? Yeah. But our sample has a difference. So what is the likelihood that we would get this sample distribution of bars all over the place if the population is equally distributed? Does that make sense? Does this sound somewhat familiar to what we've done in the past? Right? We had this whole idea of how likely is it that we would get our sample mean from a population? Remember? Week 5. Okay? During the hurricane. All right. Where would we get this expectation? Well, previous theory or research could tell us that this is something that is normally, I almost said normally, is typically evenly distributed. All right. Or we could just make an assumption. I want to highlight this idea, okay? Expected frequencies. It does not have to be equal, okay? That's a different bullet point. We can expect, we can have an expectation based upon some knowledge of likelihood. How many people are there in the room? 2, 4, 6, 8, 10, 12, 14. Okay, I think there are 15. That really doesn't help. Anybody got any money they'd like to bet me? Yeah, I'm not telling you. All right, let's bet a quarter. I bet you a quarter that there is at least one left-handed person in this class, but no more than 3 left-handed people.
What if you guys have the same? What if you agree?
Well, then it wouldn't work. Take that bet?
So that you think there's more?
I think there's anywhere from 1, 2, or 3 left-handed people in this room, but no more than 3 and no less than 1. You agree? All right. She'll take that bet. Raise your hand if you're left-handed. Yes! You owe me a quarter. We're good for it. All right. I'd feel bad if I took your quarter, if you only have a nickel. All right. Why? Why was I so confident to bet a quarter that there was at least one left-handed person in this room? Do you know what the rate of left-handedness in the population is? It's about 10%. Okay? So I figured in having 15 people in the room, well, 14 since I know I'm not left-handed, that at least one of you would be left-handed. This finally worked, because last year that I tried to do this, it didn't work so well. Okay? So previous theory or research should tell me that left-handedness is about a 10% chance. Right? And you know too much when you hope that your children don't grow up to be left-handed kids. Sorry, Cody. See? Okay. Why don't I want my kids to be left-handed? What's so bad about being left-handed, Cody? He's like, nothing. It's fine. You're just being a jerk.
One time where they talked about how left-handed imagery was like for evil, and then I was the only left-handed kid in the class.
There you go. The social stigma of being left-handed. All right. The inability to write without smearing your notes across the page as you write. See? Inability to use scissors as a kid.
I feel like I've noticed left-handed people usually use pencils, so it kind of makes sense.
Ooh, maybe there's a little secret out there. I don't know. Okay. So understanding what's in the population can give us expectations about the likelihood of what we see in our sample versus what we expect. Okay. So here's that data that was in the bar chart, because bar charts are useless. We got to use it in an actual frequency distribution table. Alpha, beta, gamma, delta. And we see that it's not 25% across the board. The alphas and gammas are higher than the betas and the deltas. Now we have a sample size of 600 people. How likely is it that we have observed this, given that it's a sample from a population? Okay. What we're going to calculate in order to determine this is called the chi-square statistic. And this is not hard, but it could be tedious. Okay, so the x with the extra little squiggly in it is known as a chi. It's the Greek x. It's actually the Greek k, but they don't have a k. Their k is something else. Anyways, it's not an x. It's a chi. Chi squared is equal to, that's a big sigma. It's just a summation sign. There's nothing special about that sigma. You're going to take the frequency observed. F stands for frequency. The subscript O means observed. You're going to subtract that from the frequency expected. You're going to square it. And then you'll divide that by the frequency expected. And then you'll sum that number up for every observation. So this is going to be a by observation or a by category calculation. Will somebody explain to me why if you get a negative number you've really screwed up? Right, because there's a squared there. And if you have a negative number and you've squared it, it better be a positive number. Okay, so there will be no negative chi-squares. We have this distance between observed and expected. It's kind of like the mean, where if you summed up every difference between frequency observed and expected, it would equal out to 0, which is why we square it. Okay? Okay. Frequency observed, this is the count. Right? So this is the number that you observe in the category. So going back, sorry, this is what we have observed. We have observed 251 alphas, 65 betas, 194 gammas, and 78 deltas. if these character traits were evenly distributed, how many should we expect to have observed? So what should that number be? $588 is the total number. Think about it for a second. We have 4 categories. There's 588. If we would expect those categories to be evenly distributed, equally among the 4 categories, what number would we have? We would have what? What's 194, Allie? It's what? You sure about that? How is 4 times 4, 18? Well, it's got to end in an 8. 588 divided by 4 is 147, actually. 588 divided by 4, 147. It's okay. It's been a long semester. Frequency expected is equal to n divided by the number of categories. If what? If and only if you what? Are expecting what type of categories? Why did I just take the total number and divide it by 4 here? Because I expected the category size to be equal. What if, just throwing this out there, what if I expected there to be a split and that 90% would be alphas and 10% would be betas? What would I do then? I'd have to adjust my expectations, right? So back in the example with the class, I expected 10% of the class to be left-handed. So I took 15 and I said, what's 10% of 15? It's 1.5. That's why I did somewhere between 1 and 3. Well, I did the 3 because I was greedy. Really wanted to win. Okay. So just the calculation of the frequency expected is dependent upon how you expect these to be distributed among the categories. Okay. So the frequency observed was 251. Frequency expected was 147. The gap between the 2 categories, the difference, was 104. You do this for every category. Okay. And then you just keep doing more columns. So the next column will be this thing squared. Okay. 104 squared is 10, 18, 16. And then what's the next step? We we divide that by the frequency expected. So we're going to take 10, 18, 16 and divide it by 147. Okay. So here's this written out in a very long way. Honestly, when I'm doing it in like a homework or something, or if I'm doing this by hand, I just like adding another column. Just keep going through and adding columns. This looks like a mess. Like, you'd get anxiety if I said do that. You're like, I don't have enough fingers and toes. Columns is just, yeah, it's just go right across and do it step by step. And then when you have a summation sign, you just add all the numbers in the column. So if you go through this, right, the square of the difference for each of the four, you go through, you notice the negative numbers exist because they're the ones that were lower than expected, but we're going to square those and those are going to go away. You add those all up, divide them all by 147. You get a chi-squared of 166.74. That's your chi-squared. Okay, now what? It's a little bit different than your other distributions. Okay? We need to make we need one more thing to figure out how to use this. And it's our old friend degrees of freedom. This concept that's out there that we don't really quite understand, but we just follow it anyways because it's how you use the chart. For the chi-square, for this, it does not matter what your n is. What matters is how many groups you have. So the degrees of freedom for this chi-square test is the number of groups minus 1. Why do we minus 1? Because we've used these groups to calculate a statistic. We've calculated one statistic out of this, the chi-square. So with 3 degrees of freedom, you'll also notice one more thing about this table. You have lots of options for what level, what power you want to have your alpha set to. All right, where are you going to reject? In this class, I've told you what? What's our sort of percentage that we want in the tails? 0.05, okay? So if we look, there's no, let's see, where's the 0.05? It is the 4th column from the end. Put a little star over that one. But Professor Wood, isn't this a two-tailed test? No, it's not a two-tailed test because this is not a symmetrical distribution. If you look at the picture, which is why I like the tables that I give you, you notice that it packs all of the significance in one tail. So the difference when you're using a chi-square from when you're using a z or a t table is where is the area of rejection. Chi-square, the area of rejection, is packed into the one tail. So with 3 degrees of freedom, we go down. I always forget for the people listening on the video that I need to, here we go. Oh, that's awful. So for 3 degrees of freedom at 0.05, it's 7815. Is 160 something or other greater than 7.815? Yes. So we would reject the null hypothesis that this is somehow that this sample is from a population of equal group size. Okay. So do you have an equal chance of being an alpha, beta, a gamma, or a delta? No, you don't. The data we collected, what we observed, is different from that expectation. This is just an example to teach you what this chi-squared is. There's one more complication to this. This is just comparing a sample from the population. You can't do this in your papers because you need to have an independent variable and a dependent variable. Let's get to the children's study. Let's mess with some kids. The test you really want to use in your papers, if you have two nominal variables, an independent and a dependent variable, is called a chi-square test of independence. Here's an example. Let's scare some children. You have a child. You show them a picture of either an angry face or a happy face. I'm not sure if it's like actual pictures of people or just like angry squiggly line face and smiley fine. I don't know. Then you say pick a toy. They have a choice between a red, a green, or a gray toy. And then you record the child's color preference. What is some of the assumptions here that the researchers are making? That they'll associate a face with a color. Why? Like left-handed people. Sorry. That was just for Cody. Okay. So her theory is that dark colors, that if you anger a kid, they'll grab a dark colored toy. And if you make a happy face, they'll grab a bright colored toy. Anybody want to disagree with that? Like, what is your expectations? If I give you an angry face, which's the dark color up there, by the way? Is gray the dark color, like the blah? You think angry goes with red? Okay. Okay. So what is the happy face going to get, though? Okay. What's gray then? Sort of happy, but not really. We don't have that, right? We only have two groups. Happy face and angry face. You have those ambivalent kids that just don't care. They just want a toy, right? Okay. So let's go through this. They did this to children. The independent variable is what face they were given. So 20 kids were given a happy face, and 20 kids were shown an angry face. The 20 kids that were given a happy face, 15 of them selected a red toy. 2 selected a green toy, and 3 selected a gray toy. Of the 20 kids who received an angry face, 6 chose a red toy, 7 chose a green toy, and 7 chose a gray toy. Overall, if you combine the two groups together, 21 kids, more than half, chose a red toy, 9 a green, and 10 a gray. Here's a stupid bar chart. if the face had no effect on the color selection, what should these bars look like? Question mark. Josh, what should they look like? They should be equally tall, right? Right? We should have 3 bars of equal height. There's one other assumption there, though, too. I made 2 assumptions. One, I said that we assume that they're equally distributed. What's the second assumption we're kind of making when we do that? We made an assumption about the face. What are we also making an assumption about? That color choice, right? That children don't care what color the toys are. If we made an assumption that children do care about the color of the toys, how could we reflect that in there? No. Preference, we're removing the facial expression, right? Because the assumption with the facial expression is that there is a linkage between face and color. I'm saying we've made an assumption about the color by drawing the lines that way. Nobody interrupted me and said, wait a minute, Wood, you're doing it wrong. What about this? So now I have to interrupt and say, wait a minute. Think of the colors. I would really hope that these toys are all the same, that these different colored toys are all the same toy. Because I might just choose the gray ball because I want to play with a ball and not the fact that I like it because it's gray. Right? I don't know. I don't remember. All right? Think of a kid. You put 3 things in front of them. One's green, one's red, one's gray. Do you assume that they would take any of those toys equally based upon the color? Well, if you do that, you are. Right? You're making an assumption about the color choice as well. And I thought kids liked bright colors. I don't know. I give up trying to understand my kids. Okay. Just if we had a different expectation, what could we do? We could say gray toys, nobody likes gray toys. All right? So we could say that it's going to be 40, 40, 20. If we have that expectation. Just like I expected there to be 10% left-handed people. Okay? I was just basically pointing out that you don't have to always assume that it's equal distribution, not distribution, equal preference among categories. But you have an expectation. That's why it's frequency expected, not frequency equal across everything. Frequency expected. If you have different expectations based upon previous research, genetics, right? Raise your hand if you have blue eyes. There's 3 of us. No, you don't get to change your vote. Right? There's 3 of us out of 15 people in the room with blue eyes. Why only that? Why only 1 out of 5 people? Are blue eyes easy to get? Let me just tell you they're not. You got to basically have 2 blue-eyed parents, or one of them can be a green-eyed parent. But if you got 2 parents that have brown eyes and you got a kid with blue eyes, something's not right there. At least that's what I remember from 7th grade genetics. Okay. So we're going to do a test about this color priming thing. Or no, it's not the color priming. It's the angry face priming. Right? Does face priming exist? Let's test this. Our null hypothesis says the 2 variables are independent. that there is no effect of face on color choice of the toys. Our alternative hypothesis, and what they're testing, is if children can be primed. This is what this phenomenon is known as. It's known as priming. Can I do something immediately before I give you a choice to influence your choice? We do this all the time, and you don't even know that you're being primed. It can be as subtle as when a salesperson comes up to you, they're told what to say to you to get you to buy something. Right? Anybody ever work retail and have that sort of training where they're like, hey, you need to talk to the customers in this way? You ever wondered why? It's because they've done research on priming effects. Okay, and what do you say? Yeah. Okay. So this is an area of research known as priming. Believe it or not, when we don't do in-person course evaluations anymore, it used to be I'd have to come to class with a huge packet of paper and then leave the room for 15 minutes, and then somebody would have to truck them all over to Edwards. We don't do that anymore. They're all now online. But there's research that shows that faculty can prime their students before they give out course evaluations. And if you do this, you will routinely, regularly get higher course evaluations. My favorite one is providing chocolate. So if I came in here and like had a big bowl of chocolate and be like, hey everybody, I got some leftover candy, feel free to grab some before class. And then, oh, by the way, we're going to do an evaluation. My chocolate scores would be higher. But hard candy's worthless. Like if you got old people candy, butterscotch and mints and that kind of stuff, that stuff's worthless. That does not prime a student to give a faculty member higher teaching evaluations. Again, there's a whole line of research on this effect. If I wore a tie, I don't wear ties because I have a neck, but if I wore a tie on the first day of class, faculty who wear ties on the first day of class, even if I don't wear another tie for the rest of the semester, have higher student teaching evaluations than those who don't. Because I have primed you with an expectation of the class from the very first day. Like, I saw that and I'm like, shit, I'm going to wear my robes. Like, I'm going to come down in full regalia. Like, that must really increase. If just a tie will increase my scores, imagine if I came down here in my robes, like Dumbledore. Okay, so that's priming. We're going to see if priming can be done with these little kids. Following the research process, we'll calculate our statistics, set alpha, find out what our decision rule is going to be, make a decision whether or not to reject the null hypothesis or not based upon significance. If you're a stargazer, we can talk about levels of significance. All right, so the first thing is degrees of freedom. This is a little bit different, right? Because we're not just having 4 categories. Now we have 3 categories, 3 rows times 2 columns. So the degrees of freedom is going to be a combination of rows and columns minus 1. So the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. Because even though we're calculating one statistic, we're doing it for 2 variables. So we got to pull out 2 degrees of freedom there. 3 minus 1 is 2. 2 minus 1 is 2. We have 2 degrees of freedom. So when we look at our table, for 2 degrees of freedom, if we set alpha to 0.05, what is going to be our test statistic? 2 degrees of freedom. It's going to be what? 5.991. So for an alpha of 0.05 with 2 degrees of freedom, the critical value is 0.5991. If our chi-square is greater than 0.5991, we're going to reject the null hypothesis that says there's no priming effect. Right? Okay. This is where it gets a little hairy, because for each of those 6 cells, we have to calculate what we would expect from those cells. And it's not just as simple as taking the total number and dividing by like 6 or something. It doesn't quite work that way. We have 6 cells. The way that I like to think about this is in terms of coordinates. This is row 1, column 1. Okay. These are coordinates. This works well. The reason I came up with this is because there's this thing called matrix algebra. When you take a data set and you treat it as, don't worry about it. In matrix algebra, they use rows and columns just like this. It just makes intuitive sense to me. So that's row 1, column 1. This is row 2, row 3. This is still column 1. This is row 1, row 2, row 3, column 2, column 2, column 2. We're also going to have totals for our rows and our columns. This is row 1, column 1 plus row 1, column 2. Row 2, column 1 plus row 2, column 2. Row 3, column 1 plus row 3, column 2. This is row 1, column 2 plus row 2, column 2 plus row 3, column 3, 2. Sorry. These 3 numbers together. And this is row 1, column 1 plus row 2, column 1 plus row 3, column 1. This is where you make the stupid mistake. Right? This is where you forget to add a couple of numbers together. It's not how you make your chi-square negative. I still can't explain that one. But this is where you're likely to make a common mistake. And it sucks because you know what? It's just addition. That's all you're doing. You'll make a mistake adding 3 numbers together. Can you believe that? It's so frustrating. It's probably why we invented calculators and computers, so that we wouldn't make stupid mistakes when we add 3 numbers together. Okay. So this is how I like to think of this. So to get your frequency expected, you take the row total, you multiply it by the column total, and you divide by the total number of n. Now you can come about n in one of 2 ways. You can add these 3 numbers together, or you can add these 2 numbers together to get n. And just so you can like double check, they should equal the same. If you add the 3 rows together, it should be the same number as adding the 2 columns together. This thing, this 2 by 2 table, is known as, or actually it's 2 by 3, sorry. 3 by 2, whatever. is known as a contingency table. It's also been called a crosstabs or cross-tabulation. There are a couple of different names for it. So how did we figure this out? Well, let's go back to our actual data. So for the happy red cell, we observe 15. We expect 10.5. Why? Because it's row total times column total divided by total total. All right. And you'll notice that across the rows, we have equal numbers. That's okay. If you find symmetry, sometimes it's okay. You might want to double check it, but in the end, lots of times we end up with symmetry. Especially when you've designed your experiment to have equal groups. And that's the only reason this happened, is because the number of kids that got the happy face and the angry face were the same. Okay. So doing all of that very simple busy work gives you the frequency expected for each cell. So now you can calculate in the chi-square the difference between the frequency observed and the frequency expected. So you're going to take 15 and subtract 10.5. Or, like the textbook wants you to do, you can write out this long-ass equation. I don't like doing it like this. I really don't. So frequency observed, I'll keep it in the cell. Frequency observed minus frequency expected is 4.5. Right? I really like this to be, I'd like to have this across 6 lines. What do we do next? We square it. So what is 4.5 squared? And then we're going to divide it by the frequency expected, which is 10.5. So that's why when you look at this, it's the gap squared divided by the frequency expected. Each cell, or at least each row in this instance, has a different frequency expected. So you got, again, you just have to be careful when you're plugging numbers in that you've chosen the right number. So you walk through this. And you get a chi-square of 8.24. What does that mean? We're going to reject the null hypothesis that there's no priming effect, which is going to lead us to conclude that what? That children can be primed, right? The frequencies representing the color preferences of red, green, or gray, 40 infants. Man, social scientists are mean. 40 infants shown either a happy or angry face were analyzing using chi-square test of independence. This analysis found a statistically significant relationship between toy color selection and face priming, such that the distribution of the 3 toy colors is different for infants shown the happy face versus the angry face. Now, let's think about this for a second. We didn't prove as much as we thought we did, but we have at least proven, or at least, oh, proven's a hard word. Shouldn't have used that. Bad me. We can at least conclude that there is a priming effect. What haven't we proven? Well, we haven't proven what the priming effect is. Okay? Now, what would we think the priming effect is by looking at the data? Try to reach, there's 2 different conclusions I'd like you to try to reach using this data. You've been hired by a company that makes toys. You've been hired by Toys R Us. And the children walk in the store. Does it matter whether or not Jeffrey the giraffe has an angry face or a happy face? Well, it depends what you're trying to do, I guess. But does Jeffrey did rest in peace, Jeffrey? Did Jeffrey have a happy face or an angry face? He had a happy face. Have you ever? How many mascots have you seen that have angry faces? Can you think of any? I mean, Sparty's a smug son of a bitch, but I mean, he can at least look happy by bouncing around and dancing, right? You don't see a lot of mascots with angry faces. Right? Like, look at Chauncey. Does he have an angry face? Beaks are hard. It's hard to tell tone from a beak. Okay. I don't think angry faces work really well. Because look at how that's distributed. I don't think angry faces work very well. Would I make that conclusion based off of just this analysis? No. The next stats class you take will actually allow you to test very specifically for effects. But all we're testing here is whether or not the concept of priming is reflected here, right? So my first conclusion that I would reach is I'd say if you're trying an angry prime, you're probably not going to be very successful. Now, I will give those 20 infants credit. They all picked a toy. Like, none of them were scared so much that they're like, no, I can't possibly. All right, I gotta go calm down for a little bit. That sign freaked me out, man. Can't play right now. So that's one conclusion that I could preliminarily make, but would require further analysis. What's the other thing? Let's look at the happy. Back to our color association. Happy kids like what kind of toys? Stop it. Look at the numbers. Happy kids like what color toys? Red toys. Happy kids like red toys. What famous toys are red? Elmo. That son of a bitch. Any other famous children's toys that are pretty much exclusively in one color? Fire trucks. Although, to be fair, fire trucks aren't all red, but Conways are white and green. Famous kids' toys. Radio Flyer Wagon, red. I actually have a couple of red bikes in my garage. Here's my all-time favorite, the Etch-a-Sketch. That's a stupid toy. I got one in my house. I have two in my house, actually. I got a big one and I got a little one. They're red. Why? Priming. Who else is red that's going to come visit soon? Santa. All right. Usually red in nature is a different kind of warning device. If you see a red snake, what do you think you should do? Run. Right? Red, you're dead. Why do you think we have stop signs be red? Stop lights be red? Sirens are red. When you're an adult, the priming effect is different. Why? Because of nature. Right? Don't eat the red berries. They're poisonous, unless they're raspberries. Oh, I'm so confused. Damn it, nature. Right? Shiny red apple. Which the adult witch turned into or evil queen, sorry, who happened to be a witch, turned into a poisonous apple, but the teenage Snow White was like, ooh, red and shiny. Like, there's a reason they didn't pick a Granny Smith apple. Priming. We like red things. Except when we're adults and we're not so playful, and then we're like, ooh, red, I'll pay attention to that. It gets our attention. Red ink. Which is not to be mean, it's just for a high contrast between black and white, but still. Okay. So there's actual people that study color and the effect of color for a living. And we sell you based upon color. Everything from kids' toys to the paint on the wall. Not this paint, this is awful. Right? Color affects mood. It just does. This color here is affecting my mood. Looks like puke. I don't know why we do this. There are actually nicer, brighter yellows that will like make you happy. Okay? I know this because the Home Depot commercials keep telling me to go there to buy the bright, happy paint. Okay? There's also reasons why you don't... Have you ever seen a car in this color yellow? I have a thing against yellow cars in general, but like yellow cars are the cars that they thought happy people would buy, but nobody wants to buy a yellow car. You've never seen a car this color yellow. And you really should not see cars these color browns. But, you know, somebody's, you got to give a color discount for some people. So when they decide to make a car, sometimes there are sports cars that are exclusively what color? Red. Ferrari has a signature red color. It's kind of like that Tiffany's blue. Right? It is a signature Ferrari red. There's a same thing, a Mustang is red. Right? Cherry red. Chevy has a tone of red. Right? I had a red car. Like, shit, I fell for it. Okay? When the cars are limited in the colors that you can get, they know this. They know this. Okay? They want to help you buy a car. Right? How can I help you complete your purchase today? With the assumption that you will be purchasing something today. All right. So that's the ChiSquare test of independence. It looks complicated, but it's really not. All you're doing is comparing these different categories and columns and rows, what we observe compared to what we would expect if there were no relationship. All right. There's one last thing. This is in the book. You can do this for your paper if you want. I don't think I don't really push this in like the exams or anything, but there is this test out there for effect size. Again, social scientists generally care whether or not the effect exists or not, and not how big the size is. There's a test known as Kramer's phi, or phi, depending upon how you pronounce that Greek letter. It's easy to calculate. You take the chi-square, you divide it by the total number of observations times k minus 1, where k is the, and this is really stupid, the smaller of the number of rows or columns. And here's the reason why that is. Chi-square is not testing for directionality. And when I say directionality, I don't mean positive or negative. I mean whether or not color and the things that we know sequentially happen, right? Whether or not the face leads to a change in color. And this is where some people can get messed up. In the chi-square, it doesn't matter if you put the independent variable in the rows or the columns. Other tests it does, and it matters quite a bit. But for a chi-square, it doesn't matter. It doesn't assume directionality of effect. It doesn't know. Like, the math is not influenced if you put the wrong variable in the wrong position. The math is the same either way. So that's why it says the smaller of the number of rows or columns. For some statistical processes, it does matter which one is the row and which one is the column. This one, it doesn't matter. And you guys have a hard time understanding what an independent and a dependent variable is. Like you really do. And so I just want to let you know, it doesn't matter. Okay? With the chi-square, it doesn't matter. It's just looking at these two things and saying, are they independent from each other? All right. So this chi-square was 8. It's above our 5.991. We're in that region of rejection. As you look across the row on your chi-square table, it also gives you for the higher powered tests with a smaller probability. And so we could go out to 0.0001, whatever the table gives us. Right, we haven't broken that threshold, but again, we don't matter. Social scientists don't matter. Don't care. Doesn't matter to us whether or not how much significance is there. We just want to know if we can reject the null hypothesis or not. That's what we want to do. That's what a chi-square is. When you're doing data, okay, when you are looking through the data set and you find some variables that you think are interesting and they're both nominal, I want you to think about something. Think about a categorical nominal variable that has tons of options, like religion. And think about simplifying it and making it easier on yourself. Is there really a difference between a Lutheran, a Protestant, and an Episcopalian? The people who practice that religion say, yes, there is. There's a reason I'm not a Lutheran. I like to dance. And Lutherans don't like to dance or drink or have fun. Not a Lutheran. Okay? Look at your categories and ask yourself, can I simplify this? Could I take all the Protestants and put them together? All right? Or am I just trying to go with, like, believes in Jesus, believes in Buddha, believes in Allah? Like, do I want to simplify it that way? Do I want to take some of these other categories and just put them into, like, the weird category? Like those people out there who are Jedis? Yep. The Satanists who sued Netflix. Yes. There's a Sabrina the Teenage Witch, which is not the show you're thinking of. It's a different show. But they actually have Satan worshiping, and they copied their version of the Satan goat god guy. And they sued Netflix. Because they did. Here's the best thing. You know what they won from Netflix? A disclaimer on the show that says the church doesn't approve of how they portray Satanists. Because that's what they were worried about. They were worried that their Satanist church would be seen as sponsoring Serena by the worst Sabrina or whatever her name is, right? I don't know. No, those are the Pentecostals. Don't hang out with them. They speak in tongues. All right, so the reason I want to end on this is because you should be at this point. If you haven't started yet, you've got 2 weeks to work on your paper. You should be looking at data. That data can be recoded. All right, I show you how to recode the data in Excel. You actually can do it in the SDA website. For those of you who came in late, I will have one more class, optional, next Tuesday, this room, this usual time. And I will work through how you would do some of this stuff, not necessarily by hand, but using the computer, using the website. I can answer specific questions about your paper, although you don't want to be that person that takes up the whole class. Okay? Because we're not doing Johan's paper in this class. We'll answer questions about it, but we're not doing your paper. Sound good? Okay. I will send out an email tomorrow reminding those who didn't come to class. I will also come up with some extended office hours for finals week, so you can come and talk to me about your paper then and final exam. The last thing, there's already is a study guide up on Moodle for the final exam, so you should be good to go there.